If you want to build a spacecraft today and visit every planet in the solar system, you have to look past the straight lines of science fiction and face the constraints of modern engineering. This map shows a system of constant, complex motion. Earth is hurtling around the sun at over 100,000 kilometers per hour, while every other planet follows a unique curved path at its own specific velocity. Reaching Jupiter requires calculating exactly where the planet will be years after launch. It's like trying to hit a moving target with a dart from the back of a moving car. Out here, fuel is an unforgiving resource. We launch with the exact amount of gas needed to arrive through the most efficient path possible, leaving zero margin for a wrong turn or a missed calculation. To successfully visit every planet, we have to stop fighting the universe and start using gravity to steer. Breaking free of Earth's gravity requires immense energy. A modern rocket burns through an Olympic-sized swimming pool of fuel every single second just to cross the line into outer space. But the hardest planetary destination to reach with all that thrust is our closest neighbor, Mercury. Traveling towards the center of the solar system is like rolling a ball down a steep funnel into the sun's massive gravity well. The deeper you go, the harder the sun pulls, causing your ship to accelerate uncontrollably. If you arrive with too much speed, you blow right past the target. NASA's Mariner 10 reached Mercury in just 5 months by falling down that hill, but it was traveling far too fast to ever achieve orbit. Modern probes spend 5 years bouncing between Earth and Venus, using the gravity of those planets to safely bleed off enough speed to actually stay at Mercury once they arrive. Contrast that struggle with Venus. We can arrive there in 5 months because its atmosphere is dense enough to provide aerodynamic braking, slowing the ship down naturally. In the inner solar system, every maneuver is a battle to survive the sun's gravitational pull. Heading outward toward Mars, the physics flip. We are now fighting gravity to climb up and away from the sun. Using a Hohmann transfer orbit, we wait for a precise 2-year alignment between Earth and Mars. Then we accelerate just enough to push our spacecraft out along a simple, curved path. Because Mars travels much slower than Earth, our spacecraft will still be approaching at dangerous speeds when the orbits finally intersect. Mars lacks a dense atmosphere to slow us down. To achieve orbit, we rely entirely on our engines, burning fuel to kill our velocity over a rocky, desolate landscape. This 8-month trip represents the absolute limit of fuel efficiency over arrival speed. Jupiter marks a staggering leap in scale. It sits 5 times further from the sun than Earth, requiring a total shift in strategy. Jupiter's mass is so great it acts like a second sun. As our ship enters its local gravity well, it accelerates rapidly toward the clouds. Capturing into Jupiter's orbit requires incredible stopping power. The Juno probe had to fire its main engine for 35 minutes straight, just to lose enough speed to be caught by the planet's gravity. Beyond Jupiter, distances are too vast for engine fuel to bridge. We intentionally bypass orbital capture and use Jupiter's gravity to slingshot our ship toward Saturn. The coasting times are immense: 7 years to reach Saturn, 13 years to Uranus, and 15 years to finally intercept the deep blue bands of Neptune. Reaching the dwarf planet Pluto takes nearly 20 years. We have to travel to the very edge of the solar system just to match the dwarf planet's incredibly sluggish orbital speed. Navigating the outer solar system requires surrendering entirely to orbital momentum over the course of decades. If we tally up the consecutive travel time to hit every stop on this planetary itinerary, the result reframes our perspective on space. Successfully navigating and orbiting every major body in the solar system using modern technology takes just over 64 years. This 64-year timeline demands extreme patience and absolute conservation, far beyond the reach of simple engineering. Tonight, look up and see the night sky as it truly is, a vast mechanism in perpetual motion. These planets are mathematically perfect, constantly moving targets. Successfully reaching every one of them is the work of an entire lifetime.